Hả? Sinh viên. Ok. Oscar. Okay. Maybe we'll start. Hello, hello. Is the mic signal? Hello, hello, hello. Okay, okay. And good morning, everyone. So midterm exam next week, Monday. 3:30 to 5:30. Link in 3. Come earlier, maybe come at least 3:15. If everyone can reach 10 minutes early, maybe we have meeting times before the exam. And then on the exam, make sure you bring your student card. Okay, bring your stationery. You can bring calculators, but I'm not sure if it is useful or not. Bring digital one, but not classical. And no dictionaries and other electronic devices. Any breach instructions or any form of cheating will result in the casing of you out of the exam hall. Have you guys been to Limit 3 before? Yes. Oh, okay. Huh? Okay. So because there will be 3 groups taking the exam together. So you guys are Wednesday. Maybe you occupy this lane here. So one row should be like about 30. I think about 60 of you. So maybe it will take up to like 5 row, 5 point a little bit, 5.2 or 5.2. Okay. But just follow the instruction of that there. I think I will write on the whiteboard just in case. Okay. In any case, you guys should sit in the same block. Okay. So DMT will sit in DMT, and then Tuesday will you are AIT, right? Yeah, AIT will sit with AIT, and then Tuesday group will sit with Tuesday group, and Thursday group will sit with Thursday group. Okay. Which one is the front? Do you know? Like this is the front or this is the front? The whiteboard is here. I think this is the front. But we'll see on that day. Just come earlier so that. Okay. So on your exam table, so you should put your student card on the left, and then there will be attendance slip from the answer booklets. So after you fill it, you can fill it down so that we can take attendance. The implementator. You can bring your stationaries without bags, no bags, only stationery. Water bottle, okay. Clear water bottle, okay. Clear water bottle. If you want to bring bags, you bring a plastic bag or what? Just clear bags. And then you will be given exam papers, answer booklet, draft paper. Okay. So you can answer in the booklet paper and then use draft paper to do some working. Yeah, that's all for the exam. Some common mistake or some laws that I want to remind you. So if you have to use this law in the exam, you can name it as a conditional disjunction equivalency. Okay. I think there's no name in the textbook, but in the exercise then name it. Okay, you can use this. So another one is a common mistake made between the set theory and propositional logic. So the cap is for the intersection, and then the head is for the conjunction. So make sure you only put sets beside intersection, and then beside conjunction, you only put proposition. Don't put set beside conjunction. Well, there's no set S and set T. Okay. And also don't put intersection, don't put proposition beside intersection. what is a proposition intercept in a proposition? Okay. Any other question regarding the exam or lectures? Okay, another announcement is there will be extra office hour this week, Thursday 2 to 6. Any clash with your timetables or not? Hmm? So this office hour is the Tuesday on the midterm week. So I move it to this week. So next week I have no office hour because just finished exam. 2 to 6, is it okay for you guys? If you want to come and find me or what? If tomorrow too many people come on this time, maybe we will move to a classroom. But I will put a notice outside my room if you come anytime. So tomorrow 2 to 6, I'll be available if you want to have some last question first. Okay. By the way, is Li 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 Jinghan here? Li Jinghan. He didn't take the quiz last week. Huh? Okay. Just to confirm. Okay. Any other problems or not? No. Okay, now we will start dive into this week lectures. So last week we do some number theory, modular arithmetic, and this week we'll do cryptography, but we'll continue on congruence first. So this week we'll be solving linear congruence. Is in the we have come across solving the linear system of equation, right? So now today we will solve linear congruence. Okay. So our goal today is the Chinese remainder theorem. So the motivation is there's an ancient Chinese general called Sun Tzu. Okay. So Sun Tzu want to know how many troops he has after a battle. Okay. So he arranged three ways. Arranges three ways. Three ways. Arrange the troop in three ways. Arrange his troop in three ways. And then he found out that his troop is around 1,000 to 2,000. So how he do? So he can't count one by one, right? So it's 1,000. So first, he asked the troop to arrange in a row of nine. Okay. So the troops will align in a row of nine. Okay. And then there's one left over. Okay. And then second, he arranged them in a row of 10. Okay. And then the leftover is 5. Then he do the third way. He arranged them at 2. Arrange them in a row of 11. Okay, and then the leftover is 1. So from these three equation, he can count that he has around 1,000 and between 1,000 and 2,000 troops. So after today's lecture, you should know how many troops he has exactly. Yeah. So next. Okay. So should I remind you how to compute modular arithmetic? Maybe just recall how to do the modular arithmetic. Otherwise, I think you'll get lost in today's lecture. So some quick question. Let's see. Let's compute 15x plus 7y. Anyone know what is 15x plus 7y mod 5? No? Again, anyone know? Maybe, okay, I don't want to spend. Okay, how, anyone know how to compute this? Two y. Okay, so why is it 2y? Huh? It's a first. Okay, so from last week lecture, right, if you want to compute the sum, modulo of sum, you can just do mod on, okay. So you can do mod 5 on 15x. You also can do mod 5 on 7y first. Okay. So to do mod 5 of 15x, what you can do is you do mod 5 individually on 15x and x. Okay. Okay. So what's 15 mod 5? So 5 is divisible by 5. That means the remainder is 0. Okay. And then x, I don't know what is it, just give it x. Similarly for 7y, you will do it for 7 divided by 5. What's the remainder? 2. Okay. And then y just give it as 1. So the answer is 0x plus 2y, which is 2y. Not 5. Okay. I'm sure you know how to do modular arithmetic. Today we will heavily depend on the collection. Okay. Any question or not on this modular arithmetic? Okay. Okay. Next. So next, we want to find the inverse of the number, right? So for example, what is the inverse of the inverse? For it A of maybe omega of 5 mod 7. Yeah. So what's the inverse is? Inverse meaning the multiplicative inverse. So it means there's this an A, then in that mod 7, such that 5 times A is congruent to 1 mod 7. Or you can do it the other way because it's commutative. So I remind you what is Z subscript 7 is. So it's the set containing 0, 1, 2, up to 7. So is there a number A, but multiply with 5 that's congruent to 1 mod 7. Is there such a number? So it's not 7. It's 6. What's the number in 0 to 6 that multiply 5 to get 1? This 6 number to test, right? 3, 3. Yeah, 3. Yeah. So let's try. So 5 is 3. Mod 7. So 5 times 3 is 15 mod 7, which is equal to, so 15 divided by 7, the remainder is 1. Yeah. So 3 is the first of 5 mod 7. Okay. Okay, good. So when does the inverse exist? It turns out that only when the GCD between M and A is 1. So let me write up. So if GCD of A and M is 1, M is greater than 1, then there exists an inverse, a unique one. A, oh, A, the unique. Okay, unique up to modulo M. Okay, that is what A inverse A is congruent to 1, congruent to A inverse mod M. Okay. So just now we only did it by inspection. So we just test number. But actually there's a systematic way to do it, which is taught by this proof here. So remember last week we learned the Euclidean algorithm. Okay. Euclidean algorithm teach you how to find the GCD between two numbers. And then we also learned the extended Euclidean algorithm. Yeah, I call it EEA here. Extended Euclidean algorithm. So that you can work backward and then express the GCD in terms of the original two uh, numbers. So we can make full use of this Euclidean algorithm since we know the GCD of AM, okay, which is equal to 1. And then we can express the GCD in terms of AM again. Okay. So since we only care about modulo M, right? How about we take this equation modulo M, right? So let's see what we did. Since so we just take this equation modulo M. Okay. So once we take this modulo M, okay, we don't know about this SA term. 1 modulo M is still 1 modulo M. But this term here contains M, right? So this term is divisible by M. So the remainder is, what's the remainder of Tm divided by M? 0. Okay, so this one, this term here cancel. So left with SA mod. Okay. So what is SA mod M? So S is the inverse of A. So consequently, S is an inverse of A mod. Okay. Okay. So what's the another use of this linear congruence here? So no, having inverse here. So for example, what are the solution of Okay. So let's say we want to solve this. So we need to solve it until we can tell x is what, right? So the question is how to remove the 3, right? Just now we see that the inverse of 3 is 5, right? So we can multiply 5 on both sides. Okay. And then you get 15x is equivalent to 24. Okay. And then 15 mod 7 is 1. So left with 1 times x, which is x. And then the other side, you're left with 6. Okay. So it will help you to remove the coefficient in front of x. Okay, so we're ready to go into the Chinese remainder theorem. What's the Chinese remainder theorem? So let's have m i's of pairwise relatively prime positive integer. Pairwise relatively prime. So meaning the GCD of any two of them is 1. Than 1. And some arbitrary numbers a1 up to an in Z. Then the claim is the system of x a1 from up to x mod an has a unique solution. But this solution is only modular up to the product of mi. Okay. So we will just write out a proof sketch. So just construct the solution. So let the capital Mi to be the little mi divided by m, the little mi. Okay. And then let mi bar be the inverse of mi. Okay. So to show the existence of this modulo mi, so little mi. So to show the existence of inverse, right? So we need to make sure that the GCD of the capital Mi and little mi is 1. Okay. But notice that the capital Mi doesn't contain M1 because I take out M1 from the product of Mi. And then I also know that all the other primes that exist here is pairwise relatively prime with the other primes. So there is no common divisor between capital Mi and capital Mi. Okay, that's why the inverse exists due to the theorem we proved in the start. Okay. So we can construct the solution as x equal to a1 times m1 times m1 bar plus a2 and m2 bar plus a2 and so on up to an. Okay. Yeah. Okay. So I claim that this solution work. Okay. So maybe let's check on one of them. Okay, because all of them look the same. So let's check on one of them. If you take this solution, okay, this solution, remember this one you need to take up to more below n. Okay, product of m1. So I claim that this is the solution that solve all these n system, the system of n linear congruence. So let's check one of them. Okay, let's do some checking. Let's check what is x modulo m mi. Right. So check x modulo mi. Is it equal to a1 modulo m1? Right. So do this check again. So if you want to take modulo mi, so notice that other than m1, right, m2 up to mn, m2 up to mn, all of them contain m1, right? Because m2 is a product of mi, taking away the little mi, which is not equal to 1, right? So all of these contain m1, little m1. So they are all 0, mod m1, okay? So only this term will survive because this term doesn't have m1. But the product of capital M1 and M1 bar is mod 1 M1, little M1, right? Because this is how we construct the capital M1. So what we'll get is x is equivalent to A1 times 1, which is A1. Okay? If you are not following, that's fine because we will do one example to show you how to use this theorem here. And let's say we have this example here. So, for example, we want to solve the following. And let's try to solve this system of congruence. So before using Chinese variant theorem, you need to make sure that this tree number is pairwise relative parameters. So we'll try to solve this linear congruence. That means we will find x mod the product of m1, little m1, so which is 3 times 5 by 7. Okay. So following the notation in the proof, so we have little m equals to 3 times 5 times 7, which is 105. Okay. And then capital M1 is m divided by 3, which is 5 times 7. Okay. And then M2 is m divided by 5, which is 3 times 7. And then M3, and then 3 is m divided by 7, which is 3 times 5. Okay. So the next task is to compute what is the inverse of this guy mod little m1. So what's this number here? So this is mod little mi, right? So let's try and reduce this number to little mi. So what is 35 mod 3? 35 mod 3 is 2 mod 3. So what is 21 mod 5? is 1 mod. And then y is 15 mod 7, which is 1 mod 7. Okay. So this 3, 5, 7 is the little mi. Okay? And then what numbers multiply 2 will get 1 mod 2, which is 2. Okay. What number times 1 is 1 mod 5? Just 1. Is M3 times M3 is M3 bar times 1. Yeah. Okay. So that you see is what am I doing is M1 bar times M1 more is equal to 2 times 2 mod 3 mod 2, which is 4 mod 3, which is 1 mod 3. Okay. So this is trying to show you that M1 bar is the inverse of M1. Okay. So what's the solution just now? Again, so I put the solution back into the board here. So the solution is you take x, okay, take x, plus the solution is x, congruence to A1. What is A1 in this case is 2. Okay. M1 is 2, no, M1 you need to take this M1 again, not modulo 3. So M1 is 35. And you take this one, 21, 35, then multiply by 2. So what is 2? So 2 plus 3 times 21 times 1 plus 2 times 15 times 1, which is equal to 233 mod 105, which is also congruent to 23 mod 100. Okay. Okay. Any question on this example? Any question on the example? Any question on this example? This example you don't need to know because exam will have this kind of question. Any question on this example? Yep. Huh? Say again. 233. Uh-huh. 233. Is it 23? 233 mod 105, is it? What's the difference? No, I just reduce it. They are the same. I mean, are you like asking why it appears? Why it appears to them? For example, I write this one, and this one is the same. Yeah. Like this. Or you want to okay. Okay. Yeah, they are the same. Yeah. Yeah, this number is unique modulo 3 times 5 times 7. Okay. You cannot have the exact x unless the question has some context that fix the x between, maybe if I say find x in between 200 and 250, then this x have to be 233. Okay. If the x is in between 20 and 30, then this x is 23. Only when there's some context you can find the exact x. Otherwise, it's just unique modulo 105. Any other question around? Not estimation, but because you live in the world of congruence, so in congruence there are like infinitely number are the same. Okay. Any other question? That's it. Okay. So the second example is maybe how to solve a single linear congruence using Chinese remainder theorem. So how to solve a single linear congruence? Okay. So if we use the method at the start just now, we should find the inverse first, okay? So that we can remove this 17. But this question is mod 276. So there are 276 number for you. So maybe it's a bit hard to find the inverse. But since you learn the Chinese remainder theorem, right? So if the solution, if there's a solution to this, if there's a solution to modulo product of primes, again, so you can go backward and reduce it to a system of linear congruence. Okay. So for example, in this case, so since you can break down the n into product of primes, okay. So by the Chinese remainder theorem, this is equivalent to 17x modulo 9 mod 3 and 17x modulo 9 mod 4 17x modulo 9 mod. Okay, and then you can simplify this equation using the modular arithmetic. So 17 divided by 3 left over is 2. Okay, but 2, there's an inverse as this, so you can cancel the 2. So I do it one by step, one by one. Okay, let me write out what is the end product first. Then I will show you. Okay, so for the first one, so you get 17x modulo 9 mod 3 is equivalent to 2x modulo, because 9 is divisible by 3, so you get 0 mod 3. So how to go from 2x congruent 0 mod 3 to x mod the x congruent to 0? So you multiply 2 on both sides. Then you get 4x congruent to 0, which is x congruent to 0. Because 4 divided by 3 left over is 1. Okay. Similarly, you do the same to the other equation. So instead of okay, you can use Chinese remainder theorem to solve this. There's another method shown in the book, so it's a more traditional one. I mean, from the definition. It's called the back substitution method. So one, you can use Chinese to try use the solution. Chinese method. Second, we will use the back substitution. This one is longer, but maybe more intuitive. So what is back substitution method? So first of all, this solution need to satisfy x congruent to 0, not 3, right? Okay, so what does this mean? So this means this number is a multiple of 3. Because when you divide by 3, you get 0. So we can have x equal to 3k, which is k z. Okay. Then you sub this equation back to the second congruence. What do you get? So you get 3k is congruent to 1. So basically you sub this equation into it. So what is 3k's congruent to 1 mod 4? So since 3 and 4, the GCD is 1, GCD of 3 and 4 is 1, so the inverse exists. So the inverse is 3. So you can multiply 3 on both sides, and then 9 divided by 4 left 1. And then 3 times 3 on the other side. So this means that k is actually 3 plus the multiple of j. So j, okay? Because this means if you divide k by 4, the leftover, the remainder is 3. Okay? Then you can substitute again. You can substitute back again. Which is 9 plus 10j. Okay? So we found a solution that satisfies these two congruences now. So to satisfy the third congruence, you substitute the x back to the third congruence. So what you get is it's 17 times 9 plus 12j, okay, equal to 9 mod 3. Okay, what you get is 200 mod j, which is congruent to 22. Okay, and then you can do some simplification to get j is congruent to 2 mod 3. Okay. So from here you can see that this j, okay, maybe I add some not here. So how how how, how to turn this negative number to positive? So maybe I do some example here. So for example, you want to figure out what is minus 2 mod 5. Okay. So what's minus 2 mod 5? So minus 2 mod 5 means when you add the minus 2 to 2, you get 0 mod 5. Okay. So what's the number you add to 2 that you can get 0 mod 5? Hmm? What is 0 in 5, mod 5 modulo? So to get 5, you need to be the multiple of 5, right? So 2 plus what number you get multiple of 5? Huh? 7? 7? 7, huh? 7 plus 2 is 9. Yeah. 2, 3, yeah. So minus 2 mod 5 is 3. Okay. So similarly, you can find this. Okay. Then continue J. So J. So in this case, so we have J equals to, so J is equal to 2 plus multiple of 2. Then you substitute back the J into the X. Okay. X is equal to 9 plus, so 2, which is 33 plus 176. So your final answer is like mod 276, right? So let's see the 276 appearing here. So that is, we have X is modulo 33, 276. Okay? Yeah, in the last minute, maybe I try another method. So there's another method, finding the inverse, right? So you don't need to do, okay. So maybe you want to check the inspection. Okay, fine. You can find inverse by inspection in most, like when the number is small. But when the number is large, you should perform the extended Euclidean algorithm as suggested in the proof of the finding inverse by EEM. So extended Euclidean algorithm. So how to find the inverse? So you want to express the GCD of 276 with 17, right? Okay. So you should do Euclidean algorithm first. And this is the tutorial question in last week. This kind of problem, you should have done it. Otherwise, you wouldn't know what you're doing now. Okay. So you found the GCD of 276 and 17, and then you express one in term of the 217 by doing the also called the back substitution. So you find the remainder and then you sub the remainder back. Okay. So what you get is okay, which is like 6. There's a 4 times 4 times plus 65 times 17. Okay. So this one, which is, if I take mod, the question is mod 276, right? So if I take mod 276, I get 65. 1 is congruent to 65 times 17 mod 276. Okay. So that means 17, okay, multiplied by 65, you get 1 mod 276. Okay. So in this case, what you can do is, we have 17x, which is modulo 1, is congruent to what? 9, 176. Okay, you can multiply 65 on both sides. 65. 65. Okay, and then we know that 65 times 17 is 1. So the left hand side becomes x. And then the right hand side is 585, 176. It's congruent to 33. So the answer. Okay. Yeah, there's few ways to solve the linear for this question. Any other question? Yeah. 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 So printing in green, red. Where this? Okay. This one. You mean this one? Uh-huh. You mean this one? You mean how to go from here to here? Because okay, so you want to compute what is f for x mod 3, right? Okay. So from the last week theorem, we just need to know what is 4 mod 3 and x mod 3. So 4 mod 3 is 1. X mod 3 is x. So 1 times x is, yeah. Okay. So if you want to compute what's the product mod 3, you just need to single individually. Yeah. Similarly for sum, if you want to compute sum, then you can just do mod individually. So everything can split in twos. That's what we proved last week. That's a tutorial question, I think. Also last week, if you use the right method. Any other question before we break? Take a break. Questions? Okay. If you have more questions later, we can answer again. You can think during the break. Let's take a break until 10:05.它只要是电脑插电，就是充电方面，对对对，因为这个 M 到就这个，它只要是 pairwise relativity，就是说任意拿两个，它们的 GCD 是1。比如说这个里面啊，你看啊这3个啊，你如果算这个 GCD 有35的话，它是1；37的话，它是1；17的话，所以他们没有。对。
那我这个人在选的时候，就是我可以随便选几个，只要是之前定为问题的，最后是预算。
结果是说，就是不是它的结果是这个 system of linear currents 有一个答案，有一个 solution，但是当然你选不一样的 MI 就不一样的结果，但是它结果是它有一个答案。你上星期有了？还没有注意到。
这边也是没这个是画的，是画的光来给还有一个就是画那个这个都是大概讲不也差不多。今天节目就是有点 SMB 啊，最后因为我们其实这个那个不加或不加都是一样的。这个是不加或者加一样的。
对，上次有讲过这个课题，所以不加其实不可以，但是如果他不加，你应该也要知道他在说什么。
不加，反正
它只有一种写法，因为如果你要写这三个空人，对不对？第一是它是一定要是 在一个 modular 的世界，就是这一句话一定是告诉你是这一个，它只有一种解读方式，
就是 x mod 3等于 q mod 3，
那个是什么意思？
就是就是它解读成 x mod。
你说不，你刚才问我的是这一个跟这个什么差别，对不对？OK，这个是另外一件事情。这个两个，这个其实是错的。我想说是这个其实是错的，但是呢，你想要解读这个只有一种方式解读，就是这个嘛。所以如果有或没有挂号都是可以，因为它这一个符号是三。对，
那这里为什么要有3条？这个那不是22？我觉得就是上那个加个对。
OK，
我有点搞不清楚。
可以，我知道你讲吗？但是我是说，我知道你等一下聊，看一下讲，
看上面写的嘛。
对，我知道这个，OK，我知道，
这个，
你说放等于跟放那个什么差？还是你要说，我可以放等于，但是我也可以放3条，还是你想问什么时候放等于什么？
对，就是有点
什么时候
搞混了。
？OK，当你要放等于的时候，不是它是一个数的等于，但是我如果放这个的话，它是 modulo 3的等于。
就是从这个来说，它既可以放等于，也可以放三条。
Yes。但是到最后的时候，看你要什么。但是这个我最后是要这个 congruence，所以我一定要3条到最后。你看像这里我就放等于，因为这是确实的一个数嘛，对不对？但是到这里我就放3条，因为我要让它，我要看它在这个congruence 的世界里，这个 modulo 的世界，所以我就放3条。当我没有看的时候，我就让它在正常的。
所以它其实它这个写的话，写的是那个我这个因为它好像就是难找出来的。
两种方法，这里一的你本身哦，小数目你可以猜哦，就是 test bar 哦，就是找判定系列等于一的啦。哪一个？没有，这个是 Euclidean algorithm 是这样子的，你可以这样子找，你也可以拿来猜来看，懂什么意思吗？有点，好，这样我直接做给你看了。OK， 你说讲找这个 M18嘛，对不对？所以这边是推说你为什么2 work， 这个是说你为什么2 work， 所以为什么2 work 呢 ？OK， 不是，所以你看啊，你要找什么东西乘2 mod 3， 2乘2等于1 mod 3，对不对 ？OK， 但是这个世界里面只有3个号码，你可以试吧，所以你试一下就知道是哪一个。什么号码？什么号码乘2会拿到1 mod 3？哦，左边那是4啊。是不一定，你只要是一个号码是1 mod 3就行，但是4是1 mod 3，明白？重点是1 mod 3。对，所以你可以试0哦，0乘2是0，就不是1 mod 3了，1乘2，所以是2 mod 3哦，2乘2 4哦，4是。如果你要用刚才那个 Euclidean algorithm 的话，你可以写3等于2乘2乘1乘对1乘2加1对，所以1等于3减1乘2嘛，所以这个 mod 3的话得到减1乘2 mod 3，OK， 所以什么叫做减1 mod 3呢？减1 mod 3是什么意思？是一个号码加去1，它会拿到0 mod 3，什么东西加1是0 mod 3啊？1加什么号码是0 mod 3？一加一加2，所以2咯。所以意思说2乘2等于1 mod 3，所以2是它的多少？
吓不到
啊？
我不理解。
哪一个不理解？
你刚刚讲
要从头讲哦。哪一个？这个还是这个？这个哪个地方啊？所以 negative 的意思是什么？
不知道。
比如说减一 mod 3的意思就是说，它是1加这个减1过后等于0 mod 3。所以1加什么号码，你会拿到0 mod 3。没有1加1等于多少？2 mod 3是什么？还是2啊？2，所以不是0 mod 3，我要0 mod 3。
这不是负1啊？
什么叫负1？
哪个？
啊，对啊，哪个地方？
所以它要加1。
没有，不是，negative 是一个号码，that 你加图它本身的那个号码的时候，不是本身，就是加图它的那个 positive of 它的号码的时候是0，懂我意思？可以来。就是做一个 inverse， 对 inverse 就是 inverse，它是 additive inverse， 所以什么是减 a？ 减 a 是一个号码的，你 add to a 的时候，你会拿到0。OK， 但是现在我们是活在一个 congruence 的 world 里面，所以我们要 mod 在一个 m， 可以吗？所以现在的问题是1加减1 mod 0 mod 3，所以我现在问你这个减1是谁？1加什么号码是 congruence 0？
1加2，
对啊，2咯，所以2是那个 inverse 哦，明白吗 ？Yes， 可以吗？
我是说
是0 mod 3不是1 mod 3。Sorry， 0 mod 3，对啊，0 mod 3，0 mod 3，0 mod 3就是0啊，我就是要0啊，我不是要0吗？我要0啊。
所以3
1加2是3，
1加2是3啊，
是
3
0啊。
3 mod 3就0。
3除3剩下什么？
0，
所以是0 mod 3。
可是这里后面是0 mod 3，不是3 mod 3。
可以，我可以写3 mod 3，3 mod 3跟0 mod 3是一样的东西。 它们是一样的。
哦，3除以3没有余嘛，
对
余数。后面
对
这个是余数来的
对
，remainder。
对，3mod 3跟0mod 3是一样的，跟6mod 3是一样的，跟9mod 3是一样的，跟300mod 3也是一样的。
因为后面出来是 remainder，不是讲那个数目。
OK 啊，
应该
老师刚才那个上面那个
哪一个？呀，
黄色的啊，这个乘起来是什么呀？
这个 A1 呢？A1，你拿 A1，
啊哈，
OK，乘你的 M1，然后再乘你的 M1 吧，然后再加 AI2 乘你的 M2。
那老师，这个我要讲，
哎，这个
哦，
这个我要讲我怎样知道是A1 A2 A3是什么？就这个，
就
这怎样知道是2、3跟2？我这样算出来。
没有，这是题目，这是题目，这是题目，
题目给
这是题目。
因为上面有一个是要乘的，
哦，你是说
下面的
下面的？你是说涨价的？那你做涨价的？
不是，它就是一个 number，然后200多，
啊，对啊，
哦有
276
啊
对啊，
啊，对，
对啊，276嘛，
对，是怎样展开？我
这个
讲
怎样展开啊？
啊
这怎样展开啊？
啊，
这怎样展开？哦，OK，这个怎样展开？这个展开，如果你
因为有很多号码我可以
是拿 prime 嘛，拿 prime 嘛
OK，上次有一个快速的方法，就是
根号
every positive integer has a prime divisor that less than square root n。
啊，对，
所以你就是从
就
square
一个一个找。
根号
，yeah prime less than square root n 开始
4是 prime
啊，就是你
4是余了，最后可能我找到23跟3，然后
然后我就选3个最低的，
3个最低没有，你要把它拆到完，
看到我
拆到完，然后有很多的话要怎样选上？
没有讲很多啦，一定算得出来。
啊，没有，可能你要4个、5个、6个都有可能，耶，不一定3个，不一定3个，
去做多一点的那边。
耶，
这个只要 reduce，
这个 reduce，
这个等于2乘105加23，
106这样的还是那个6 mod 3等于0 mod 3。
耶，所以这个除105是什么？
没有啊，
除一下，你
2乘105加23，算一下是不是这个数字？
140，
啊，应该是除一下就可以懂了，因为
最后因为我们这边是看余数嘛，
你105除233，
210 23，
所以就是要除到拿那个 remainder 显示。
yes，但是我们的看法每次都是这样了，2乘这样，我们就没有这个东西在脑里面啊，这个看你哪一个方便你想。
然后这个还可以更大啦，就是看它 x 的 ring。
对，你可以一直加 multiple of meaning。
这个可以变
到最低。
通常
simplify 到最低，
他就说23，这么不要写个33，
上也可以。
可以，
你要看它的 range 啊，因为这个是最 common 的嘛，因为它不一定是2乘105，它可能是3乘105、4乘105。
最好是 Chinese remainder theorem 是要讲什么？一开始是要做什么？
就这一行嘛。
哦，
什么叫一开始？
就是
一开始要 solve 一些 system 哦。
它其实最后要找的是那个 x。
对，
然后
就 x 等于
就是如果有一个题目的话，它是要讲开始要做什么？
这边357，先把它的那个 mod 拿出来乘，你就拿到一个 m。
357是什么东西？
mod 3、mod 5、mod 7，
这个是题目给的，
这是它的 system 嘛？
这是它 system。
哦，所以这个是题目来的。
对，
好 OK，
他题目啊，哎，要不要坐下来问？
然后你看
坐下来问。
m 乘357就160，然后算 m1 m2。
可能这个是让老师可以讲多一次。
讲多一次哈 ，OK， 我再讲多一次。有的时候，等一下问，晚上问。 Okay. Yeah, you got a lot of questions. So now I will explain the slide again, then make sure you ask any question. Okay, stupid question are allowed. Any stupid question. Okay. So what Chinese remainder theorem is doing is you are given a system of congruence. So these are given. Okay. So the goal is to find X that works, that can solve these three congruence. Okay. And then the suggestion is you find this X here using this formula here. Okay, so you need to know what is AI, what is M1, what is M1 bar. Okay. So AI is given in the question. Okay. And then M1 is this by this construction here. So you take the product and then you take away the corresponding primes or not, either primes or not primes. And then okay, so you follow this recipe here. So you find your A1, find your M1, find your M1 bar, and then you take the sum of them, and then modulo M. Okay. So which part you don't know how to find? Maybe A1 or M1 or M1 bar. Which part that you are not familiar with? Huh? Whole part. Okay, so first we settle what is AI, right? So AI, first you need to make your system of linear congruence into this form first. So it's a mono, this like the coefficient of X is 1. Okay. And then this number here will become your AI. Okay, so this is your AI. Right? Okay. So in this question here, in this particular example here, you have A1, A2, and A3. So your A1 is 2, A2 is 3, A3 is 2. That's why I got 2, 3, 2 here. Okay. Second, you need to find the capital MI. MI, yeah. So what's capital MI? So capital MI is you take the product of the little MI and then divide it with the corresponding M. Maybe I use MJ. So for example, what is M1? Okay. M1 is you take the product of 3 times 5 times 7, okay, divided by the first MI, divided by 3. So which you get 35. Okay with 35 or not? Okay. Then similarly, this is how you get the M2, M3. Okay. So you take the product, divide by 5, you get M2. Take the product, divide by 7, get M3. Okay, so this is how you get the capital M1, M2, and M2. But how to get this is you need to use the modular arithmetic. Okay, so this is some technical part here which you learned last week and this week. So how to find the inverse of M1? Okay, but the inverse we care about is only up to modular little mi. Okay, so for example, M1 bar. Okay. This is the inverse of M1 modulo 3. Okay, modulo this M1 here. M1, yeah. Okay. So I think you guys a bit maybe I'll recall. So we recall the inverse thing. Okay. So let's recall the inverse. Let me resize this. Okay. So recall what is multiplicative inverse first. Okay. So multiplicative inverse here means, for example, 2 times half equals to 1, right? But now we care about the congruence, the modular arithmetic. So for example, let's try mod 2. Okay. So in the real number world, you just take fraction, right? 2 times half is 1. But what is half in modular 3, for example? Okay. So in modular 3, half is one number that multiply 2 that you get that is congruent to 1 mod 3. Okay, so what's the number that you can multiply to 2 that you get 1 mod 3? Huh? 2, right? So if you take 2 times 2, you get 4. What is 4 mod 3? 4 mod 3 is 1. Because 4 divided by 3, the remainder is 1. Yeah. So the number is, so I mean, I want to show you that the inverse is another number. Yeah. So in this case here, you already found M1. Okay. So what number multiply 35? You get 1 mod 3. This is what I show you. And then my suggestion is 2. So let's check. So 2 times 70 is 2 times 35 is 70. 70 mod 3 is what? 70 mod 3. What is 70 mod 3? 70 mod 3. So 70 divided by 3 is 69 mod 1 mod 3. Correct. So this is how you find the M bar. M1 bar. Okay. And then M2 bar, you do it for mod 5, and then M3 bar, you do it for mod 7. And then you take the products and then you add all of them up. Okay. This is a unique solution up to modulo the product of little m, okay, which is 105 in this case. Which part want to repeat it? Confused again. M1 bar. Okay, let me say a statement, see whether what you don't understand. So M1 bar, okay, is a number that you multiply to M1 such that you get 1 mod 3. Okay, so M1 bar is a number that you multiply to M1 that you get congruent to 1 mod. Okay, so meaning you need to know what is M1, which I already tell you how to get this one. No problem on this one already. Okay, so you got this number. Also, you got this number 3 here. Okay, so how you going to find M1 bar? How to find this number? Right? If you can find this number, this is the M1 bar. This is the inverse of M1. Okay. Any other question or not? M1 bar. Okay. If more question, just now there's one guy. What's his name? Adidas jacket. What's your name again? You got question or not? Yeah. Just now you have question. No. Okay. Okay. Let's continue. Okay. So there's two theorem or calculation that you need to know. One is Chinese remainder theorem. The other is this Fermat-Little theorem. So Fermat is a judge He's not a mathematician, but he do mathematics during his free time. His hobby is doing mathematics question, solving problems. So, what's Fermat's little theorem? So Fermat's little theorem can help you to reduce product of integers. So if the integers is not divisible by a prime, okay, then this equation here holds. So a to the power p minus 1 is congruent to 1 mod p. Okay. So the congruence is a congruence of primes. Okay, here have to be primes, must be prime. Chinese remainder theorem doesn't say that all the mi has to be prime, just need to be relatively prime. Can see from this example here. This is not prime, but all of them are relatively prime. Okay. But Fermat's little theorem need primes, okay? So I put p here, must be prime. And then if you take an integer that's not divisible by p, and then raise it to the power of p minus 1, and take the prime and the minus 1, it's congruent to 1 mod p. And 1 is very good because 1 can return to the identity. So furthermore, uh, for all integers, we have a to the power p congruent to n mod p. So you can think of like multiply a on both sides. But remember, we can go from here to here using the theorem we proved last week. So if the number is GCD of AP is 1, then we can just cancel one of them and on both sides. Remember the theorem, not proved, but we talked about last week. Okay, so we won't prove this theorem, but how to use it is important. So how to use this? How to use it to find, for example, the remainder. So how to use this theorem here? So notice that 11 is a prime. Okay, so we are in some shape now. 11 is a prime. So let's factor the 10 out so that we can reduce this prime to 1. So for example, we can take out the 10, how many of them? 22 of them plus 2. Okay, which is 7 to the 10, 22 times 7 to the 2. And then by the Fermat's little theorem, okay, 7 to the 10 is 1 mod 11. So which is 1 2 times 72 mod 11. So which is equal to 49 mod 11, which is equal to 1. 49 divided by 11, then what's the remainder? What's the remainder? 49 mod 11. 5. Okay. Yeah. So 5 mod 11. Okay. So if you use the second one, you also can use the second one. So let's see. So 7, 222 is also equal to 7 to the 11 times what? 20. 20? Yeah, 20 plus 2 again. So by FLT again, Fermat's little theorem, you get 7 to the 20 plus 2. Okay, you can further break the 20 again, so 11 plus 9 plus 2. Right? Correct? That right? Yeah. So this is let me see. So this is actually 7, 2. Okay. So by Fermat's little theorem again, this is 7, 7, 9 plus 17. This is 5. Again. Then you can combine them again. And get 7 times 7. Wait, this one I moved down, which is 29. Which is okay. So in your mind, this should keep inside your mind this formula here. Yeah. So the formula here you need to keep in mind. So a to the prime minus 1 is congruent to 1 mod p, and a to the p is congruent to a mod p. Okay. Then you just try to apply. We got tutorial question to help you familiarize with these population. Okay. Okay. So in the last period here, so we will do cryptography. Okay. So cryptography is you want to communicate some message or sentences between two of you secretly. So when you pass a message, you won't write a letter and then pass it, because if it lost in some path, then people will get to know the message. So how are you going to switch encrypt the message? So a crypto system, you start with a plain text message, and then you want to cipher the text message. So you get a cipher text message. You want to encrypt it with some sort of key, and then you can use that key to decrypt the message. There are few crypto systems. For example, the first one is the shift cipher, is a Caesar cipher. So Caesar, I think, is the king. So the king also used this cipher method here. So you can associate every A, B, C, D, E, F, G, so the alphabet, with the number from 0 to 25. So it's a mod 26 system. And then you can shift all the number by, for example, by 3. Okay, any number within mod 26. So for example, you have a plain text, maybe say very good. So you change all these number into the integers again. And then let's say your shift cipher is shift the number by 3. Okay. So you shift the number by 3, and then you turn it back to the cipher text. And then you pass it to the other person. Okay. And then that person, how to decipher? Take this message, put it back to numbers, and then -3. And then put it back to text. Okay. So this is the first kind of crypto. The second cipher is, instead of just shifting the number, you can multiply the number, then add. So how it works is you need to measure the GCD of the number you multiply with 26 is co-prime, so that the inverse exists. Then the inverse exists, then you can find the inverse function, right? So if you got this number here, and then you take away b, and then you multiply by inverse, then you will return the original number. Okay. So this is the GCD of A, and 26 is 1 is very important, so that you can find the inverse. Okay. Remember just now we find a lot of inverse with GCD 1. Okay. And then the third one is a block cipher. So just now the key is what? This key is the shift. This key is the shift and the scalar. Okay. And then this key is a block of number, a block of letters, yeah, or number, because these letters will represent some numbers here. Okay. So once you got this key, you can split your text into block of this key. If this key is like 5, 6, 7 longer, letters longer, then you will split into a 5, 6, 7 longer respectively. So in this case, it's 4. So you split very good into a block of 4, and then they will shift differently. based on this number here. Okay. And then how to shift it back? You just apply the inverse of the shift. Okay. Yeah. So for the shift cipher and the affine cipher here, and then also the block cipher here, this is called public key cryptography, because anyone know the key can just decipher or encrypt the message. Okay, so only between you and the person can know the key. If any other person know the key, they will know how to encrypt and decrypt. But the fourth one is the RSA crypto system. Is a public key cryptography. Everyone can know the key, but they might not know how to decrypt it. Okay, everyone can know the key. So we'll see why can everyone know the key, but not all of them can decrypt it. So RSA cryptography is done by 3 persons with the initial R, S, and A from MIT. So what's the key here? So the key here is a number N and a number E. Okay, what's the number N? The number N have to be a product of primes. Okay, the product of primes here they're interested is in a large prime. Okay, many digit primes. Okay, and then you take the product and become your N. And what is E? E is have to satisfy this weird condition here, which is the E, the GCD of E and the product of P minus 1 and Q minus 1 is 1. Okay. Okay, so from here you should think that there's some inverse going on here, right? So let's see how it works. And then there's P minus 1 and Q minus 1 here. Prime minus 1, right? Just now appear in the Fermat's-Slater theorem. Okay. So somehow these things have to work together. Okay, but first of all, how to encrypt the system using this public key? So you've also convert your alphabet into integer, but now it's a 2-digit integer. So for example, 0 becomes 00, 1 becomes 01, 2 becomes 02. Okay, 2-digit integers. And then you will group your integers based on your n. Okay, depend on your n, you will group them together. Okay, so for example, if my key is 2537, I will group my word into 2 letters block. Okay, 2 letters block. And then what I do next is I raise the number, the block, to the power E. Okay, so E is the power you need to raise to. So for example, if I want to encrypt this stock using RSA cryptography, right, crypto system, then we turn the stock into 2-digit integers, and then I break into blocks of 2 letters, which is block of 4 digit, and then I raise it to the power E. So I raise it to the power E, and then mod the n, mod n. Again, raise to the power E, mod n. Raise to the power E, mod n. Okay. This calculation is too big, so I'm not asking you to do it. Just let you see. So and then the end product is another cipher message. Okay. But the problem is how to decrypt it. So how to decrypt it? So to decrypt it, you also raise to another power. So what's the power? So you know that the GCD of E with the product of P minus 1 and Q minus 1 is 1. So that means we can find the inverse of E again. Modulo P minus 1 and Q minus 1. Okay, we can find the inverse. Okay, but maybe you ask, hey, what's the use of finding this inverse, right? Okay, so for example, let's say we already raised to E. Okay, and then we raise to the inverse again. So it's E times E bar. And then you get 1 plus K P minus 1 times Q minus 1, because it's a multiple of P minus 1 and Q minus 1, right? So it would be good if we just left with M. Okay, so that means we need to get rid of all of this. Okay, So we need to get rid of all of this power here. So how to get rid of this? So remember we have the Fermat's little theorem, right? Fermat's little theorem. So but it's a bit different for Fermat's little theorem because here is PQ, not just P or Q, right? Okay, but that's fine, because this is the product of P and Q. Remember, we can use Chinese remainder theorem to break this system into mod P and mod Q. So let's do this this term here with P and Q first, and then see what we got. Okay. So by Fermat's little theorem, if we take m p to the minus 1 and then mod P, what we get is 1 because we raise the integer to P minus 1. Okay. Similarly, m to the power q minus 1, we get congruence to 1 mod q, okay, by Fermat's little theorem. Of course, Fermat's little theorem says m and p or m and q have to be GCD1. If not, we can solve it similarly. But just assume they are GCD1 first, then we can use Fermat's little theorem. Okay. If we can use Fermat's little theorem, then what we have is the c that raised to e bar, sorry, this should be an e bar. This should be an e bar. Change the notation. Okay. Is this congruence here, c to the e bar, okay, is actually m mod p. C to the e bar is actually m mod q. Okay. So you have a system of linear congruence here. Then because p and q are two primes, so their GCD is one relatively prime, pairwise relatively prime. So it follows from the Chinese remainder theorem that you can find the solution. Okay? And the solution is actually c to the e bar that's congruent to m mod pq. Okay? And m is your original message. So this shows that if you raise your number to the inverse, okay, you will get back your original message. Yeah. I don't think this example is quite enlightening because it's just some large inverse finding. But so why is it hard to decrypt? So what you know is this 22537 here. Okay. Only the person who hold the key know how to write into the product primes. Okay. Let's say I hand you 2537. Can you immediately find the product of primes? Right. So it's very hard to find a product of prime. And what they did is they used the billion, maybe million digit of primes, product of 2 million digit of prime. Because we have shown that there's infinitely many primes, right? So you can go very far and find primes. Okay. So to write into product of prime is hard. But if you produce a way to break numbers into product of primes, then you can break this RSA crypto system. Okay. Yeah, so if you want to yeah. If you want to hack or crack the system, if you can find the quicker way to write numbers into product primes, then this RSA crypto system will break. Okay. 10:42. Okay, we still got time. If you want me to go through the previous part also can. Because this cryptography is not important for exam. For exam, it's not important. You can read. But for exam, what's important is the for this chapter is the Euclidean algorithm, extended Euclidean algorithm, Chinese remainder theorem, and Fermat's little theorem. And then in the tutorial, we will do a lot of exercise, make sure that you can understand and then how to use them, how to apply the concept. Any question or not on the crypto or the or how to make money with crypto? Yeah. So what's the theorem? Okay.
The second way of the
Oh, okay. Okay, sure. Yeah. Okay. So there's two form of Fermat's little theorem here. So first form is a raised to the power p minus 1, you get 1 mod p. Okay. This is when the case a is not divisible by p. But another one work for all a. So it's a to the power p is congruent to a itself. So you a raised to the power p, you go back to a. Fermat's little theorem. Okay. So the second way I use this. So then I need to, since this is mod 11, so I need to break this power into 11 first. Okay. Multiple of 11. So first I break into 11 times 20 plus 2, right? So 222. And then 7 to the power 11 is congruent to 7 mod 11. So this part here becomes a 7. And then there's another 11 here. I further split the 11 out. Okay. And then this 7 to the power 11 is 7 again. And then there's 9 and 2 again. So I can add them together and then become another 11. So 7 to the power 11 is 7 mod 11. Yeah. So you left with 2 7. So 7 times 7, 49. So match up with the another calculation. Okay. Any other questions? Any other questions? Yeah. Huh? Go question. What? Never mind. Don't be shy. Go question. Which one? Which one? Which one? Never mind. It's okay. I just repeat. Which one? This one? This one? This one? Okay. So this one is what? This one is 7, 11 times 20. Right? So this one is what? This one is actually 7, 11 times 20 times of. Okay. Is it? Yeah. Correct, right? Okay. So so there are 20 of them. So each of them becomes 7. So there are 20 of them. So 7 to 20. Okay. Is it correct? Yeah. Okay. Now okay. Yeah. It's okay. Okay or not? Huh? Got question? Just ask it. Then I know what's the problem. Yeah. Up to Fermat little theorem. Yeah. Because you want to apply this theorem here, right? So this theorem only apply on power of p. How is 222 a power of p? So you need to find the p out, the power of p out first, and then reduce it. Make sense? Uh-huh. You mean you need or you don't need? Mm, if you know what you are doing, you can do it at the last. If you don't know what you are doing, make sure every time when you put this triple line here, you should put a mock. Okay. If you know what you're doing, you can just keep going until the end. Then I also will know what you're doing. But if you don't know, make sure once you see this triple line, you should actually put a mock here. Okay. Because this triple line only works under modular arithmetic. Okay. Only works under congruence. But yeah. Okay. But make sure you mention where you use this theorem. Yeah. So only the theorem with the name is important to remember. If there's no name for the theorem or corollary, then you can just use it. Yeah. Any other concern or confusion? Understanding? Okay, never mind. You can keep thinking and then we can later come back and ask again. So we can repeat. And so we'll break until 11 o'clock, and then in the break, you can come by groups to find your quiz. Okay. Come group by group so it's not congested here. Okay, so we will resume 11 o'clock. Okay. Let's get your thoughts. Okay.
讲太快了，我还在想，莫名其妙在这部分了。然后你说不重要，然后就放弃思考。
OK。OK。啊。
不要，尤其是11点的问题，特别这个。自己考试有考吗？老师？
没有。可是如果要听懂的话，可以再讲一次。
就是
啊，
等下再讲。然后你这样这些东西会给出来，这样。
如果有用的话，这个表可以。
除了那个 disjunction，
对，就有这个表可以给。
那比如说这个
啊，
这个 theory 的话，用的时候就要比如说就写出来。
对。
那这个including operator 要不要写？
要。
这个要写。
要。
这个写在哪里？因为我看你第一。
你就写by Euclidean reason 哦。哎，等一下。哦，没有哦，写在，哎，我没有写。对啊。其实也不是，如果真的是没有写，也不会怎样了，就是因为
做对就行了。
因为也只有这个方法吧。但是如果要写的话，我觉得比较好。
没有，你这些都没有 GC， 就是算 GCD 的时候。
对。
都没有写。
对啊。 如果要那我先写一个来完整版呢，所以我写在那个这个在哪里？
22，
因为那个也只是一个算法来给你们传。
这是 extended 在上面，
可以在上面。
这个
OK。说如果我真的要写的话，我是不是在课堂写？然后如果真的要写的话，我应该要这样写。sorry， 应该是有点点。然后 GCD
直接写 GA 就可以
啊，
就是1.1，然后打个点，然后再写。
没有，我先写一个最完整的给你看一下。这边可以结束啊，还是你还要再写
63就可以结束
？63也可以结束，或者你要到30。呀，最完整是这样。如果
就是考试的标准的话，就 by EA
可以啊，多写啊。
不写也可以。
不写应该可以，因为我们只有教一种方法做的。
这个 extended 这个也要写。
如果能的话就写。如果真的忘记了，方法还记得就可以。
对啊。
就是上我上次没来上
素养。
对
素养 ，OK。
就是我在这里，他是花里的，他要真的严格，他就要单调性的分。我算出来 MC 的5次减跳5次，我说我是因式分解算，它是少一点，直接另设一个 GS， 用再算这个 MC 这样。这样还是用这个因式分解式。
这个你说用或者用这个？
就是一种是我重新设一个函数，它是然后正它是利用图像来正它是单调，还是就是把这个 MC 到5次元上是因式分解的？
什么差别？
这个都跟这个很难算。
对，这个好像应该不太行。但是你这个是怎么来的？
就是跟经验
啊？跟图罢了。但是这一个不然这个我用那个 algebra 算吧。这个我只是用我在那个课堂做的那个方法来证明它是 strictly increasing。我课堂的方式。就很应该就是把 real 分成 positive 和 negative， 然后在 positive 的时候，当你取 x
是那个
上课讲的，就一样，比较嘛，明白吗？其实你只要证明 S5先，难怪你讲 S5，所以你只要证到那个 inequality S5，然后你只要两边加1就是派了，对吗？所以你只要证 S5是 strictly increasing 啊，对，所以证这个用课堂的方式比较简单，但是如果你要用这个的话，你就要去解这个东西。
这样来一个这个肯定是正的。
不一定，因为这个是有3的，对。对。
对，有点复杂，不可以。对啊，因为你不能够证明了他为什么要图片，我们只 sketch 嘛。对，但是总分3是不会气了吧？什么叫不气？就是那个什么，哦，没有，那个是总体的总体亏啊，总体亏是28%，那个是28%，这个是其中比较多，对。
这个证明是错的吗？
等一下我会解释，然后你听一听，然后你再看。
不是我好像是就是如果我用 contradiction 我证出来这个，那这个就是对的。
contradiction 你 suppose 它是错的嘛，对不对？
就是 contradiction，然后我 prove 这个不属于这个。
没有，你 contradiction 的话是你要 suppose 这个，要用这一个，然后证一些 contradiction 出来，然后才证明这是对的。可是你不是去证这个是错的，你是用这个去证一些东西是错的，这样才不是。你是这样子写的，不只是，但是
我是写的 find an element，这是 find an element，but not no such element。
很好。但是这个也不是 contradiction 啊，
我可能就
你是证它的 negation 啊，
哦，
对吧？
那我想错了，这个也是没有。
我等下再解释看看你有没有说你想一下，等下我再解释一下。对呀，
这个题它必须要用那个 proof 来证明。
什么叫用那个 proof？ 用那个 definition？
他不是说不用任何定义吗？不用任何定理，那我们学那些全是定理啊。
定义
Theorem
要用定义来说吗？定义of 什么是 definition of proper subset？
definition
of proper subset
在哪里
？proper subset
就这个 PS 的这个定义，
不是
它那个就是它的那个子集所包含的那个，就把它的子集写在一个
那个是子集啊，这个是真子集。
对啊，真子集啊，不是那个不是子集写在它的集合里面，是把它的所有子集写在一个集合里面，是这个
子集和真子集不一样。
那是它的真子集还是子集？
子集。
对啊，子集
表现是子集，可是这个是真子集。
对啊，所以那既然如此，它里面有2个元素，一个是空集，一个是它，这证明了它俩任意一个都是它的真子集。任意其中一个都是它的真子集，
不是子集。
我任意一个呀，比如说我这一个东西，我有10个子集，那么其中的任意一个都是我的子集，因为我本身有10个子集。
对呀，可是不是真子集啊，
是真子集啊，
是子集。
就是那为什么
Power subset 的 definition 是 set
对是
all
子
subset？
但我知道是子集
对啊，
但是我现在拿的是其中的一个呀，我没拿全部呀。
没有。Power subset 的 definition
对呀，
是 set of all subset。
耶，
然后里面的 element 是它的 subset， 不是它的 proper subset。
但是如果拿其中的一个呢？
其中一个，我就是拿其中一个，它的 elements 啊。
每一个都是它的子集，但是
都是它的
它也是它的真子集啊，因为它就是唯一的，不是真子集的意思就是除了它本身的，真子集是除了它本身的那一部分，剩余的，也就是说只要排除掉一个就可以了，只要把自身排除掉。但是我这
可是我们没有证明过。
但是我也没不需要证明啊，但是我没拿它本身呀，它本身是这个元素呀。
OK， 我写那个 statement 给你，我知道你讲的。11点了。
那我下课了
啊？
下课结束。
让我 解释完给他们听，
可以
然后我再解释给你看。OK，你有理，但是你有一段东西要写出来。OK， OK。Hello, hello, hello, hello. Let's come back to the quiz discussion. Okay, let's discuss the quiz first. Because I think both questions have some definition that you need to use. So if you're not familiar with the definition, maybe you think they're very hard for you. Okay, so try listen carefully and then see if you can earn more marks. Right? So I'll try to give some marks. So first of all, okay, after you listen to the this discussion, right? If you think you have more mark, you can come and find me. So first is the finding the cardinality of empty set. So by definition, empty sets contains no element. So no elements in the empty set. That means the size of the set is 0. Okay, there's no element inside the set. There's no Also the size is 0. The cardinality is 0. So some of you don't know what is cardinality, so you can't get mark. So make sure you learn all these English vocab, because in the exam you cannot bring dictionary. And also I know some of you use Chinese text to study, so make sure you have the English text to accompany you. So second, if you is to ask you to show empty set is a proper subset of set of empty set, okay, without referencing to any theorem. So I want you to prove from the definition. Okay. So what's the definition of proper subset? Two things here. So one, it is a subset. So you need to prove that the empty set is the subset of the set of empty set. Second, you need to show that they are not equal. Okay. So that means there's element in the right hand side which is not in the left hand side. Okay. So in plain mathematical symbol is for every x in the empty set, you need to show that x is in the set of empty set. And second, there exists an element in the set of empty set which is not in the empty set. Okay, so if you can write out what you need to prove, I'll give you mark here. So not even starting to prove it. So you just need to write down what you need to prove, then I'll give you marks. So how to show the first one? For every element in the empty set, it is in the set of empty set. So you need to take an element in the empty set, but there's no element in the empty set. I think we encountered this when we show that phi is a subset. Empty set is a subset of every set. Okay. So basically, I want you to reproduce the statement there. And then secondly, you can find a x in the set of empty set such that it's not in the empty set. So why is it true? Because there's only one element in the set of empty set, which is empty set. So is empty set element of empty set? No, because empty set by definition contain no elements. So this is false. So this statement is false also. Okay. But I mean, this is true, but yeah. So there's nothing in the empty set. This is true. Negation of the statement is false, but the statement is true. Okay. Yes. So basically, I want you to recall the slide here. Okay, remember this slide here? The proper subset. Primary x. The slide here. Okay, second is the function. Fx equal to 7 over x. Okay, I want you to show that it's onto but not one-to-one. You can draw picture to help your understanding, which is a good practice. So from the picture, maybe you can see that the graph actually didn't attain the 0, y equals 0. So why is it not onto? Because 7 over x, if you set your function to be equal to 0 from the codomain, it's not possible. You can't find a pre-image of x. Okay? Because you will get a contradiction that 7 equals 0. So you cannot find. So I think we did it in the tutorial question as well, in this question here, but maybe I don't write it too clear on this 1 minus 0. I just say that 1 is in R and we can't reach 1, and then I do some small calculation there, but didn't write it quite clear. So if you can mention that you can't find 0 in the codomain such that your function can reach it, you'll just get 2 marks. If you don't get 2 marks, you can come and claim from me. And then show that f is 1-to-1. We just show by definition. So what is the definition? You need to suppose fx equal to fy, and then show that y equal to x. Okay, so you just let f7 of x equal to 7 of y, and then you do some algebraic manipulation, then you get y equal to x. Okay, this is also done in the lecture, tutorial, but this function is a bit different. So it's minus 3x plus 4. So if you let minus 3x plus 4 equals to minus 3y plus 4, then x will be equal to 1. If you cancel 4 from both sides and then cancel minus 3 from both sides. Okay. And then what is 2.2 doing is, because we have seen that f is not onto on this codomain here. So I want to see whether if you chop off part of the f and see, can you find some bijective part of f if restriction of f is bijective. Okay. So actually any interval you pick apart from the interval that contains 0 is bijective. So any part you pick here will be bijective. Any part you pick here. Okay. Yeah. So 2.1, there's another way to show 1-to-1. Okay. So I heard from other students, they show it another way, which is by class, in the class, because we saw that if it is strictly increasing or strictly decreasing, then the function is 1-to-1. So if you can show this function is strictly increasing or decreasing, f is also 1-to-1. So the task becomes showing the f is strictly decreasing. Okay. So from the graph, you can see that the negative part is strictly decreasing. Okay. The positive part also strictly decreasing. Okay. So if you can show that the positive part is strictly decreasing and then the negative part is also strictly decreasing, then you also can show 1-to-1. Two ways to show 1-to-1. One is from definition. Second one is using the strictly decreasing or increasing method. We did in the class when we show the S cube is 1-to-1. Okay. Any part need to repeat or go over again? Any part you want me to go over again? Also, you take a picture of your quiz and then take a picture of your quiz and then later send me that. Hey, why there are 5 these people here? They don't take their quiz. Not here. 杨玉涵 not here. 杨玉涵. 杨玉涵 not here. Why got sign one not here? 零四乘呢？零四乘 here 咯，零四乘 not here. Also got sign 哦。I remove the sign 哦，你等下。Yeah. 好，谢谢，我也是。哎，why you not getting your quiz match？零四乘啊 ，no quiz 啊，quiz 啊，那杨玉涵 not here 啊，杨玉涵。No one is a friend of 杨玉涵。玉涵，对。Yeah. Okay, you can start doing the tutorial question and then discuss it. Hey, you say you don't understand the crypto. Even for the shift one. Okay, okay. Okay. 它全部就是把字母变去号码，然后在号码上面做东西这样。
准确来说，它到底是怎样转怎样走？不关它的 basic theory，大家都明白。
哦。因为如果 RSA 如果你要真的去算啊，那些东西数目太大了，你要用计算机还是电脑来算，所以就是知道这样。如果要真正去做，就有点。 或者还有一个想法， 它的两个圆珠这一个号码是什么？啊，这一个和这个。好，对，除了过后，的话，这个也等于，如果你把这个减掉这个过后，它可以为什么？减掉了，会把有些是减掉。那如果你拿7减1的话，六可以配上对吧？对吧？对，我忘记改了，我改另外一边忘记改这边了，所以。对，没有错，32应该没有错哎。32没错，飞到39吧，我就奇怪是谁呢？
反正有点不对劲。一个对吧？我找一下根据的一个例子，找。那个有。我这个是对89，89，34。
哦，对吧？一路放回去，上面有什么把出去了，是21，这地方的对对对，30到10，就是算出来了，推出来了，然后你再从这些反推的过程中可以找得到那个它的equation。我算了一下，我打算我上面准备一下副的材质。你们对下面还有课？没有，我是点做下一盘。我对这里就是那个压力太大，我就在说，就要睡得很干净。那个这个。从那个来源，就是感冒茶了，那个你还给吃到6滴血，昨天给我那个。对吧？中午一次，晚上一次，凌晨一次，早上一次。哎，不是比较大。程度那个时候是吧？差不多对。是的，看那个。而且你中午别了。我来不过你的 restriction， 然后我才，我看到上面有，我就测那个性质。我感觉我肯定马上他妈就是我去画他。 我昨天情况的时候，不一样的，他们多一样的。所以他们要的是个小地方。比较严重的一次会昨天演到很简单，基本上就没有训练过那个，真的是很难。不一定，后面就学谁的这个，就相当于直接去看去抽卡，我都是上过的。我喜欢是这一方。讨厌。那天哦，就是跟他聊，不他在懂他上的那种公马很好，那种拉，这个想，我想为什么你还熬不到了，而且还给你出这个？很辛苦的事情。快特别的后面。你要重考，然后Okay, let's come back to the tutorial question. So if you want to pass in the exam, you should do all the tutorial question. If you want to do good in the exam, make sure you know what concept you apply in the tutorial question, because not all the question is like just changing number. So maybe change a bit of the wording, the way I ask it. So you should know that this is corresponding to this kind of question. Okay. So when you do the tutorial question, you should ask yourself, what is the concept here? What is the definition you use or theorem you use? Okay. Okay. So what do I want to discuss here? Okay, some of you still confused with the definition of inverse here. Okay, here the inverse here refer to the multiplicative inverse. So multiplicative inverse means you need, when you multiply, you get 1 mod 200 and 2236. Okay, mod this number here. So maybe to you the division is more intuitive on the long division. Okay, I mean similar to me, but you can use a more elegant way to write this. So you can write the long division as a multiple form and the remainder form, which we call the division algorithm. Okay, so this is how you transform between long division and division algorithm. Okay. Uh, what's next? So yeah, so 4.4.6. Okay, 4.4.6 shows you that how we combine the Euclidean algorithm, extended Euclidean algorithm, and then find the inverse. Okay, find the inverse. Use this two method to find the inverse. Okay, some of you ask me, do I need to say by Euclidean algorithm or by extended Euclidean algorithm? If you can write. Okay, for completeness. But of course, I only teach you one way, so this is the only way you can use. But for completeness, you can say something like, for example, like by Euclidean algorithm, GCD of 89 and 34 is equal to GCD of 34 and 13, and then GCD of 34 and 31, sorry, and then 31 and 13, and then keep going up to GCD of 1 and 0, which is 1. Okay, for completeness, but if you don't write, also should be fine. So like this part here, you also can say by standard Euclidean algorithm. Similarly, got few similar examples. Yeah, 4.4.10, 10 is the normal one, but 4.4.20 is the Chinese parameter theorem. So all the number mi here are pairwise relatively prime to each other. So these are your AI. Okay, this is your solution, right? So AI, and then this is the M1. So M1 is the products divided by the MI. So this for M1 here is 20. M2 here is 5 times 3. And then M3 here is 4 times 3. And then you find the inverse mod MI. Okay. So for example, 2 times 20 is 40. So what is 40 mod 3? Which is 1. 1 mod 3. Okay. 40 mod 3 is 1. 40 is congruent to 1. Okay. And then 4.4.34. Okay, so you notice that this is a prime. So if it is a prime, then you can use Fermat's leader theorem. Since this is also relatively prime to 41, so you can use the Fermat leader theorem, say that if you raise this power to 40, which is 41 minus 1, then you will get 1. Okay, and then you will just reduce the remaining term. Okay, Fermat leader theorem. And then 4.4.38, we combine the Fermat's-Little theorem and Chinese remainder theorem. Okay. So Fermat's-Little theorem to simplify the equation, the congruence, I mean. Okay. Then you will see that all of them are 9 mod 5 or 9 mod 7. That should change to 9 7. Okay. And then 9 mod 11. Okay. So by Chinese remainder theorem, all together you have the answer to be 9 mod 385. Okay. So this is the application of Fermat's-Little theorem combined with Chinese remainder theorem. Got this kind of question in the 4.4.4t. So we want to show that 42 divide n to the power 7 minus n. So n is anything. Okay. So first of all, turn this question into modular arithmetic. Okay. So what do you mean by you can? So actually it's a 0 mod 42. Okay. So 42 is a product of primes. Okay. So if it is a product of primes, then you can split this congruence into linear congruence using the Chinese remainder theorem. So all of them you can find in 0 mod 7, 0 mod 2, 0 mod 3. So by Chinese remainder theorem, you can combine the solution. Okay. The next one is for you to play around with the cryptography. Anything? Yeah. 4.6.40 is also will come up, similar question will come up in the exam. So you need to know what it's doing. So if you want to talk about division or remainder, right? So you can turn into a modular solution, modular form, modular arithmetic form. So if you want to show some 35 divide n to the power 12 minus 1, then it's actually equivalent to show that n to the power 12 minus 1 is congruent to 0 mod 35. 35 is a product of primes. So you can split into further split into system of congruence using the Chinese remainder theorem, right? So and then you notice that there's 12, there's 12, and then there's some n primes, powers, okay, Fermat's-Little theorem. So Fermat's-Little theorem help you to reduce the system of congruence. Okay. So yeah. Okay. So you need to know how to combine Fermat's-Little theorem and Chinese remainder to compute all these system of linear congruence or linear congruence. Yeah. Huh?
Supplementary.
Yeah. Okay. Any question you want me to run through again? I think I will put this up tomorrow. If you so take a photo of the quiz and then return me the paper copy, and then if you want to argue for your marks, you can come and find me.哎，
这有分面这个，
什么？
这有分面这个。
你讲啊，你讲有分。你讲啊。
我也想问。
问啊问，来问。没有，你先跟我讲哪里有分，先我才可以给你分。不可能我
这种理解啊。
妈的，你觉得哪里有分啊？你跟我讲，然后我就看看点。来，
它这个错误集合的，我觉得这个就是一个是正它的子，第二个就是正它们两个不完全相等。前面正它这个不完全相等，这个是任何集合的子直接用嘛。那这个前面正它是它们两个不相等的话，那我是还少了一个，或者说它应该就是正平对应。
为什么？
就是我这个前面这两句话就证明它们两个不相等。就是
因为他们的 power set 不相等。为什么？啊，为什么这句话会说他们不相等？
就是它这个比它多一个这个原因。
你说如果看他的 power set，为什么你写的这句话会代表你刚才说？
就是它只是它这个 power set 中有一个元素，它不是两个呀，就所以说这两个不是完全相等的。就是说
说看。说看。
那这个跳过好。
没有对明高考的在里面呢，然后这个扫过哈，这是扫过哈。
OK， 扫过它，然后代表
它也在它里面了。
它也在里面，然后呢？
这不是你们
对，它在
它在它的里面，然后扫过它。它在它里面，然后扫过它。它在它里面，它扫过它。OK， 但是你写的东西啊，不是你讲的东西啊。但是如果你这样子想，的话是对的，
没毛病啊。那我就取的，
但是他不是这样写，
差不多。对，但是他取的也不是他本身，他取的是除了他本身的另一个，说明他另一个肯定是他的真值。
你说谁？你说你还是说？
这两个不一样吗？他不用 power set 吗
？OK， 你要说是因为它是它的 subset， 但是它两个的，它比较少啊，你是说，对不对？它比较小。
对。
啊，它比较小，所以它有另外一个有它没有的东西，因为它们一定肯定哪里不一样的嘛。然后一个又躲在一个里面嘛，对不对？你要懂我讲吗？懂。这是你的答案来的哦。但是你写的东西不是你讲的东西。
真的？
可以给你1分啊。
那别人
啊？给你3分。你来考一下分啊。你来解释一下你写的东西，看看有分吗？
我的不过没有了。
啊？
听我解释。
听我解释。
我听。但是你要知道你写的东西不是你讲的东西，你知道吗？
也不是讲。
你写的东西不是你讲的东西，因为你这些字全部混在一起用的。你看，这是我要你正的东西，但是你又拿来写。听得懂啊？听得懂我才给你1分，听不懂。
不要1分，怎样都听得懂。不懂也要懂，
讲给其他同学听的。
不懂也要懂哦。
不行，老师，比我嘛，就在里面。
没有，你第一个你要说这个是它的 subset 先。第一步你要说这个是它的 subset。
但是我这样就不行了，你这两句话没什么很大区别啊。
一个来，所以你第一步你要说这个是它的 subset， 然后第二步你要说的它们不一样，然后你怎么说呢？你刚才说的是因为这个的 cardinality 是1，这个 cardinality 是0，所以他们肯定是
就他扫过
啊，明白吗？
对哦。
你是我们的代表。
啊，对你只有这句话是对的罢了，这句话是要做的。Yeah，
这不能用抖音 subset
是我要你 prove 的东西。对，subset 我已经，其实我是说不可以用这个的，我其实要你说这句话也是，但是如果你懂的话就，至少你懂啊。哇，我就不知道你懂不懂啊，真的。
我真的只空完老师给我懂，我不想写嘛，我10分哦。这个狡辩我真的会耶，
可以吗？可以
我
吗？
只是现在不会，不代表以后不会是吧？
用一种灯啊，
好吧，这两句话是
哪
不一样
哪写
的，这个跟这个是不一样的。
啊，我当时不会的，我现在会了，我老师。
OK 啊
我那时会不代表现在
，OK 啊，OK 啊，
他厉害狡辩吧，他厉害狡辩吧。
我这里也应该也是不写空语，
别给你1分了啊。
那是前面的那。
冷静，
那这里就是说，它是它的子集嘛，这个是他们不一样嘛？那
哦，子集没有代表他们不一样。
没有，它这句话，它这个题要证两个，一个证它是子集，另外一个证他们两个不是完全相等嘛。
OK，可以，这个可以一分，这个可以一分。
然后后面也是，就是你可能看不懂我在写些什么样子。
你说看你说。
我把那个只是没有用那个数学语言，但是我前面说了，它这个 domain 里头是没有零，但是这个 codomain 里头是有零的，就是它这个就不是说那个定义域中所有的元素就和那个什么那个值域中它们不是完全就相等，所以我就是说那个值域能取的值是比定义域更多，所以它们不是那个 onto。我这句话就讲这个，你 onto 不是那个满设的话，就是定义域里头有多少个数，那你值域中也要有这么多个数跟它对应。那你定义域中的数少一些的话，那值域
继续，
就是
后一组我讲
继续。
所以就值域中的数比定义域中的数更多的话，就可以证明它们不是那个吗？
没有，因为我也可以有这个 example， 这个是满的，这是很多，这个多这个少，有这个情况的。
那我前面这里算不算举反例啊？我前面这句话就是举了它那个零。
可是你没有说这个方向不可以等于0，你要说这个方向不可以等于0才。
那这里算不算啊？虽然
没有啊，不是啊，你只是说 domain 不可以取0吧，但是你没有说这个方向不可以取0，它是因为这个方向不可以取0。
是
啊。
但是它这个题目中，它不是都已经把0给排掉了吗？
没有啊，这个0是说我没有这样的数字吧啊，但是我要问的是有没有这样的数字啊，明白吗？这个是 domain 来的 ，domain 是在这里下面 domain。对，然后我要是这个 core domain 的不等于
它有问题，我没有看到，我觉得好了。
可以，这个可以，
这可以啊，来看看，
还是很惨。
老师，你解释一下我的问题。
也是来解释，来不要拿去答案。
谢谢，我应该看没有，不是，我刚找东西来想。
OK， 要答案。
是这个，还是那个问题
？OK， 我知道你的问题啊，然后你现在再解释给我听。
我解释啊，我用的是 power set，power set 的定义就是把它所有的
subset
对 subset 列为一个集合里面，那么这个集合里面的所有东西都是它的 subset。
OK， 好。
然后没，然后我就取其中的一个呗。那么我可以取它本身，也可以取它的其他的部分。但是我现在不取它那个本身，因为本身的话是它就不满足分子的定义。我取